So we're gonna start with number 10. We have a big sphere with radius b, but it has a cavity in it, so it has a little hollow sphere in it with the radius a. And then the charge is in the bigger sphere of plus q. So first, we're asking for rho. And we know that rho is equal to q over v, which is equal to q over 4/3 pi r cubed. But the sphere is a big sphere and a hollow sphere. So then the r cubed, we're just gonna change it to b cubed minus a cubed. So we're kind of looking at it as two different spheres. That's how the math works for this one. And then that's our rho. So we're gonna move on to b when we're looking for the electrical field when r is less than a. So when r is like around here. And then since all the charge is not in the hollow sphere, but in the big one, it's when r is less than a, it's within the hollow sphere, so there's no charge there, so the electrical field is just gonna be equal to 0. And then we're gonna make room for c, not that we need that much. So now we're looking for the electrical field when a is less than r is less than b. So we're gonna set up the integral. So we have e dA is equal to rho dv over epsilon. So we have e times 4 pi r squared is equal to rho times 4/3 pi times r cubed minus a cubed. It's basically the same as it was here, but then since r is going to be around here, we're just going to replace b with r for that particular equation. So then we know the electrical field is just this divided by this. 4 pi's will cancel. So it's going to be equal to rho over 3 epsilon r squared, and then the r cubed minus a cubed stayed also on top. That's the answer to C. We're going to move on to D. So now we're looking for when r is greater than b. So when r is all the way out here. So we have the integral, so e times dA is equal to q over epsilon. So then we have the electric field times 4 pi r squared is equal to q over epsilon. So the electric field is just equal to q over 4 pi r squared times the epsilon, and we're just using the original volume because that sphere is not getting any bigger. So that's the answer to D. And then we're going to move on to E, where we're sketching a little graph, but I'm going to erase all this. So we have E here. So we're going to find the electric field as a function of time. Distance, so r. And we know that when r is equal to a, it's all 0. So we're going to just start here. And then it's going to go up, hit its maximum at b, and it's like kind of linear, but not really. And then the maximum is going to be q over 4 pi b squared epsilon. And then it's just going to decrease slowly because it's dependent on r squared as we found in the previous problem. So it's just going to have this little asymptotic function, and that's the graph.